Hello everybody. So what we're going to be looking at today is finding the Taylor or the Maclaurin series for a given function. Okay, and so there's kind of some theorems and stuff that we need to get to, but before we get to those, we're going to just talk about maybe a series that we haven't seen before. So what are we doing today? So one, we're going to learn what a binomial series is, or yeah. The binomial series is. The next thing we're going to do is we're going to learn how to use substitution. Now this isn't like integration substitution. This is just like algebra substitution. Learn to use substitution to find a new series from an old series that you already know. So to find a series using a series you already know. Oh, word's hard. Actually, before that, so this is out of order, we're going to look at some common series, look at series, Maclaurin series for common functions that you'll see a lot. And lastly, we're going to learn to find a new series by taking the derivative of an old series. All right, so that's what we're going to be doing. So let's start at the beginning here. We're going to learn what a binomial series is. Right? So binomial series. All right. So if you have a function like this, so let's say suppose. So suppose. I don't know what we're supposing. Let's just look at this. Here's a thing. Several things. Here's a thing. If I take 1 plus x to the 0, that's 1. Right? Anything to the 0 is 1. If I do 1 plus x to the 1, that's 1 plus x. If I do 1 plus x to the 2, that's, if you multiply it out, 1 plus 2x plus x squared. If you do 1 plus x to the 3, you get 1 plus 3x plus 3x squared plus x cubed. If you do 1 plus x to the 4th, we'll stop here, 1 plus 4x plus 6x squared plus 4x cubed plus x to the 4th. Okay, now there's a bunch of numbers here, these coefficients. I'm going to highlight them. So like there's a coefficient of 1 there that we don't write, and of course that's also a coefficient of 1. Then here you have a 1, a 2, and another 1, a 1, a 3, and a 1, a 1, a 4, a 6, a 4, and a 1 for the coefficients. Okay, and those coefficients have a particular form. So the coefficients have this form. So like you know, like the 1, 4, 6, 4, 1 that you have on that last row, they all have a particular form. Actually, I'll say formula. They have a formula that we can know. So what they are is, let's see here. The coefficient of x to the n in 1 plus x to the r, so there's an n and there's an r here, the coefficient of x to the n in 1 plus x to the r is given by this formula, Rn. So those parentheses are on top and on bottom, and it has that mathematical symbol means this. And you're going to see this mathematical symbol in other math classes, like a statistics class or something like that. Okay? Now, just to check this, we're not going to check all of them, right? But like, for example, let's check this one right here. So like, for example, that one, in 1 plus x to the 4th, right? The coefficient of x to the 3 should be, according to that formula, it's r choose n. So r is on top, r is the 4, right? R is the exponent there, so the r is a 4 for us. The n is on bottom, that's the exponent on the x, so that's a 3. Okay, so this is what it would be, 4 on top, 3 on bottom. And if you write out what that is, that's 4 factorial on top. On bottom, it should be n factorial, which is 3 factorial, and then r minus n factorial, so that's 4 minus 3 factorial. And if you work out those numbers, well, you can do it 1, 2, 3, 4 on top. On bottom, 1, 2, 3. That's because of the 3 factorial. And then 4 minus 3 is 1. So then there's a 1 factorial, or yeah, 1 factorial, which is 1. You can cancel those out. The 1, 2, 3, the 1, 2, 3. And what you're left with is simply, you can see, 4. And that's what you see up there. Right? Now, that's kind of a pain in order to do that, right? But still, you can. And the thing about it, though, is that there's a... yeah, so the thing about it is that you could make a formula out of it this way. So we could say, ooh, nope. So we can say 1 plus x to the r would be, according to the formula that we just wrote, it would be r0 times 1, r1 times x, r2 times x squared, r3 times x cubed, and you can keep doing that. You would stop until you got to, you would stop when you got to r x to the r. Okay? And then you could write that as a series this way. 1 plus x to the r would be, r goes from 0 to, n goes from 0 to r. Rn x to the n. And I'm not going to work out an example of that because that's not quite what we're trying to get to yet. But you could do that. All right. But then what we can do is we could actually extend this, because what we did here would only work if r was an integer, right? Because these factorials only make sense when r is an integer. Well, I don't know. In factorial only makes sense for integers, for positive integers actually, or at least non-negative. right? Like if I say 3 factorial, that means 1 times 2 times 3. But if I pick a different one, like if I said, well, what would 3.2 factorial be, right? That doesn't make sense. Okay, so factorials don't make sense there. But what you can do is you could actually find a formula for this thing that doesn't involve a factorial for the r. You can find a formula for r over n here that does not have a factorial of r. It'll still have a factorial of n though. So how would I do that? Well, I'm going to show you an example, and then I'll just tell you what the formula is. So here's an example. So let's look at maybe a bigger one here. Let's do like a 6 and a 2. Maybe that'll make it clear. So if I do 6 and 2, according to the formula we know with factorials, it would be 6 factorial on top, and then on bottom, it would be 2 factorial, and then 6 minus 4. No, 6 minus 2 factorial, which will be 4. 2 factorial, like that. Okay. Then what you can do is you can rewrite it where that top factorial is a 6. The bottom factorial, the 2, I'm going to leave as a factorial. Actually, I want to take that 6 factorial and write it out. Sorry. 1 times 2 times 3 times 4 times 5 times 6. And the 6 minus 2 factorial is a 4 factorial, so it's 1 times 2 times 3 times 4. Now hopefully you can see that you would be able to cancel the 1, 2, 3, 4 that appears on the top and on the bottom. And so the result here is going to be that 6 over 2 here is 6 times 5 over 2 factorial. And so there's no factorial on the top. There's no factorial that involves the 6. And so it turns out that there's a pattern here that you can exploit. So the pattern would be like this. So let's say I wanted to do like 7 and 4. What would that look like? Well, the pattern's going to be like this. So in the denominator, if the 4's on the bottom here, you're going to have a 4 factorial. Okay. Now, on the top, you're going to have what? Well, it turns out that what you're going to have is, if the bottom is 4 factorial, you're going to have 4 terms on top. The terms are going to be 7. I don't want it that way. 7 times 6 times 5 times 4. So the numbers just count down, and whatever the number is on the factorial is how many of them you have on the top, right? So like on this one, it was a 2, and there was 2 there, and then 1, 2 things up here, right? So that's a 1, 2 things. Where here, it's a 4, and then 1, 2, 3, 4. 1, 2, 3, 4. And so that's the pattern, okay? So you would be able to write those out. And so if you write that as a formula, the formula is this formula. That's not an example, the formula. So, so our definition is going to be this definition. It's going to be, if you do R and N, then what you get is on the bottom, in factorial, right? And then on the top, what you do is you start with an R, and then you do R minus 1, and then you do R minus 2, right? And you keep doing that. And, well, where do you stop? It's a little bit tricky to say where you stop, but where it is it's R minus N plus 1. That's the last number. So like, for example, up here, the R is a 7, and then the n is a 4, right? So r minus n plus 1 is 7 minus 4 plus 1. So 7 minus 4 is 3 plus 1 is 4. And that was the last number there. Okay, so it's a little bit tricky to look at, like this formula here, but this formula will work even when the top is not a factorial. The r is not an integer. So like, for example, I'll do one with a fraction. If I do, let's go 7/3, comma 4. No, I can't. It's got to be smaller. Let's do 7/3, which is a little bit bigger than 2. So let me change it here. Actually, it doesn't have to be bigger. I don't know why I said that. Let's do what did I say? 4? Let's do a 4. All right. So the way this would work is on the bottom it's a 4, so that's a 4 factorial, and that would mean on the top you have 4 terms. So the first one is 7/3. The next one is 7/3 minus 1. The next one is 7/3 minus 2. And then the next one is 7/3 minus 3, which, if you're okay at fractions, you would be able to work out pretty well and get like 7/3. 7/3 minus 1 is going to be 4/3. You're subtracting 3/3 every time. 3/3 is 1. So subtract 3 from the numerator every time, basically. 1/3, and then one more, subtract 3/3. You'll get negative 2/3. And so the numbers go negative, and that's okay. So that's how you would calculate one of those. Now, what do I want to say about it? Well, what I want to say about it is the binomial series then is going to be this. So this is actually going to be a Maclaurin series for 1 plus x to the r, and r is allowed to be a rational number, positive or negative fraction here, where r does not have to be an integer. And we do need absolute value of x to be less than 1. So what are we going to do with it? Well, I need to write it, right? So here it is. So 1 plus x to the r. And so what it looks like is this. 1 plus rx plus r minus 1 over 2 factorial, x squared, r minus 1, r minus 2, 3 factorial, x cubed, plus ... And that actually goes forever. Okay, that actually goes forever. And what happens is, if the r happens to be an integer, then at some point one of these will come up 0, right? Like if r is 5, then after the 5th term, you're going to have a 0. And so that just makes the series stop. Because up here, this series was not an infinite series. It stopped at r. And down here, I'm saying it's an infinite. It goes on forever. Well, it goes on forever, but a lot of them are 0 if r is a integer. So, positive integer. So this is n goes from 0 to infinity, rn x to the n. All right, and then again, that's if absolute value of x has to be less than 1 for that to work. Okay, so that's our Maclaurin series. Now, what are you going to have to do with it? Well, mostly what you're going to have to do with it is actually solve like a very simple question. Well, maybe not that simple, but example. Example. Let's say yeah, what's the Maclaurin series? For, let's see, 1 over, I'm going to do a square root. You actually have a cube root in your homework, which means I don't need to write that. Write out the Maclaurin series for this. Okay? And the way you would do it is very simple. So you would say, okay, well, first of all, this is actually 1 plus x to the negative 1/2, right? Square root is a 1/2 exponent. So this is your r. And then that tells you that you know the formula. It's going to be n goes from 0 to infinity of r, which is negative 1/2, n goes there, x to the n. So this much is easy, right? You're just filling in the r here. You figured out the r, it goes right there, just like it's right there. Just like it's right there. Okay? So that much is easy. What you might have to do on the homework at some point is you might have to calculate some terms here. So I'm going to say find the first, I'm going to say 3 terms. No, I'll do first 4 terms of the series, just to make sure we understand the technique here for writing it out. So it's 1 plus rx plus, and then now this is where the pattern really starts. You go r minus 1, 2 factorial, x squared. So I got 3 terms. The next term is negative 1. You know what? I'm going to start calculating these easier, right? Negative 1/2 minus 1 is actually just negative 3/2. And then negative 3/2 minus 1 is negative 5/2. I don't have to write it like this, where I write it as minus 1. I can just actually do the subtraction as I go. So minus 1 minus 1, that would be over 3 factorial x to the 3, and that keeps going, but I don't need to keep going because I said 4 terms, and this is going to be 4 terms. So then what I would recommend that you do is just grab a calculator here to calculate these things, because you've got this like negative 1/2 times negative 3/2 over 2 factorial, right? Like to calculate this, it's just easier to start using a calculator. So 1/2 times 3/2 is 3/4, of course, over 2 is 3/8. So this is going to be, 3/8 x squared. And then what's the next one? Well, you're going to have to calculate this all out. So we got 1/2 times 3/2 times 5/2, that's 4.5, over 3 factorial, which is 3/4 again. So it's 3/4. I'm going to check the sign in a second. So what should the sign there be? It looks like I have a negative times a negative times a negative, which would actually be a negative. And so there you go. And that is the first, I mean, it keeps going, but that's the first 4 terms from the Maclaurin series. So that is the binomial series. I think you really only have to do like this kind of thing. Go from here to here. But if you have to write out terms, you can do it. All right. So that is binomial series. Now, what's next? So what's next is we need to learn to start computing a series from another series. So compute a series, no, not series, every day, right? Compute a series from another series. Right, so the first thing we're going to need is we're going to need a list of series to start with. So you could come up with them yourself. We learned how to do that, but we're not. What we're going to do is we're going to look at a list. So get a list of common series, Maclaurin series, from the book or from Google. Right? So Calculus Volume 2, Section 6.4, which is, what's it called? Working with Taylor series. Is going to have this graph. So let me find it so I can give it to you. What? Okay. It's in notes. It's called there. I mean, that's not what it's called, but there it is. Okay, that wasn't that hard. Let's make it big. Okay, so here you go. Here's a list of Maclaurin series for common functions. Stop it, computer. Driving me crazy. So let me put a box around it. I hate the way that it doesn't like have a border. And then but the lines don't match up with the lines. Okay, there we go. That makes me happier. So what these are these are series that have been calculated for you. You would be able to do them, right? Like we did a series for sine x, we did a series for cosine x. We did these in the previous section. So if you ever need them, here they are. Okay, and tells you the function name, the Maclaurin series, and the interval of convergence. And the idea behind this is that you're going to be able to get new series from these by either substitution or by doing derivatives. So let's talk about substitution. So it's easiest to illustrate with an example. So let's say I want this. Let's say find the Maclaurin series for, let's say, cosine of 3x. Okay, so what you would do is this. You would start with the series for cosine because you've got a series for cosine just up here on your list. Okay, and so let's start there. Right, and I'm going to write this a couple different ways. So you could say cosine x is, and you can copy the formula, and you know the formula is fine. There's nothing wrong with the formula. Negative 1 to the n x to the 2n over 2n factorial. Let's double check that that's right. Looks right. The interval of convergence is actually negative infinity to infinity. Always converges. You're not going to need the interval of convergence for this homework, but still, you can write it. There you go. Okay, now what that series is actually, I would say, or if you want to write out the terms, feel free to write out the terms. So when you write out the terms here, this series looks like this. Nope, not series, hold on. It looks like 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial dot dot dot. That's what it looks like. So you can write it in that form or the first form. Now that's not the series that we want. We want the series with cosine 3x, right? Not x. So to get cosine 3x, just replace all x's with 3x. That's it. That's all you have to do. So you could do that either in the formula, either in this formula here. You can do that. Cosine 3x is going to be, and you just write it out again exactly the way it is. You just replace all x's with 3x. So instead of x to the 2n, it's 3x to the 2n over 2n factorial. And technically you would do this to the interval of convergence, by the way. You would just come over here and you would go, well, that's 3x in between negative infinity to infinity. But again, it doesn't really matter here. Not only could you do that, you could also substitute the 3x in here for all of these x's. Okay, if you do that, you're going to get 1 minus 3x squared over 2 factorial plus 3x to the 4th over 4 factorial plus 3x to the 6th over 6 factorial plus dot dot dot. And if you do this, a lot of time it's going to be a good idea to kind of split this power across the 3 and the x, make it look like this: 3 to the 2, x to the 2, 2 factorial, 3 to the 4, x to the 4, 4 factorial, 3 to the 6, x to the 6, 6 factorial, and so on. Oops, I made a mistake, right? Sorry about that. That should have been 3x. Cosine 3x. So if you need terms, like if they say find the first 4 terms of the series, you're going to want to do it like this. If you need the formula, of course, then you would do it like this. Knew it was going to do that. All right, so you could either do that in the basic form or like with the terms written out. So either summation notation or not, as you choose. And so this right here, you can do a lot of complicated things with this kind of idea. Like, let's do one more similar example that has one extra little trick to it. Example, find the series. I should say, I'm being lazy, I should say Maclaurin series. Find the Maclaurin series for, I'm going to say, x squared e to the negative x. Okay? Now, hopefully you have an idea of what to do here. We should start with the series for e to the x, right? Start with Maclaurin series of e to the x. So you just say e to the x is equal to, and again, you could write it out, or you can use the formula, either or. Maybe I'll do both here. So it's like this. What is it? X to the n over n factorial. X to the n over n factorial. Which, if you work it out, put in a 0, you're going to get 1 over 1. So it goes 1 plus, put in a 1, you get x over 1. X squared over 2 factorial. X to the 3 over 3 factorial. X to the 4 over 4 factorial, etc. That's what it is. All right. Now, we've got a negative x, though. So in order to get a negative x, we're going to need to replace x with negative x. So you do that. You replace x with minus x. You're going to get e to the minus x is 0 to infinity minus x to the n over n factorial. And if you work that out to see what happens here, you get 1, and you're replacing all of the x's with minus x. So I want to write this out so I can show you something. So you replace all of the x's with minus x, as I am doing. What will happen here is a negative number to the first power is negative, but a negative number to a second power is positive. So what you get is that all of the ones that were squared end up with a plus sign in front, but all the ones with a odd power are going to end up with a minus in front when you simplify it a little bit like I am doing. That should be a minus right there. All right. So there you go. So that's what that series is. Also, while we're at it, you can see that it became an alternating series. You could have seen that it became an alternating series here by splitting it into a -1 to the n, x to the n over n factorial, right? Negative x is -1x. So this is the same thing. All right, we're not done. That's e to the negative x. What are you going to do about this? Well, the x squared is just being multiplied, right? So if we just multiply both sides, we're just going to use regular algebra here. So this is a new thing, a new idea. Multiply both sides by x squared. So if you do that, on the left side, you're going to get x squared e to the minus x, of course. That's what you want. Here, you're going to get -1 to the n, x to the n. Now you're adding an x squared. Here, you have x squared times all of this. So I'm just writing it at the moment. I'm too lazy to write the next one. I'll put the dot 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 already. So then what happens is you can just use the properties of exponents to combine the x to the n and the x to the 2, and you would get 0 to infinity, -1 to the n, x to the, looks like n plus 2, in factorial. And over here, when you multiply the x squared through, you're just going to get, every power goes up by 2. So you get x squared, x cubed, x to the 4th over 2 factorial, x to the 5th over 3 factorial, plus dot dot dot, right? All the powers of x are going to go up by 2. And that's your Maclaurin series there. Again, you could write it 2 different ways. That's why I'm, writing it the way I am. You wouldn't be doing this. You wouldn't have this and this as your answer. But some questions want this and some questions want this in your homework. Okay. So that's really all there is to it as far as substituting in, right? You just write out the series with as it's originally written, and then you can change that variable to some other variable, and you just replace it over on the other side, and you get what you get. Okay, so that's substitution. Now, the next thing, which is pretty much the last thing, is going to be derivatives here. Okay, and there's kind of like a tricky problem or two in here that I want to talk about. So let's see. A new series by taking derivatives. And it's a pretty simple idea. It's just idea. if you have f of x and it's some kind of power series, I'm not even going to write it as a complicated series here. I mean, I'm not gonna like write it with like a formula here. If you have that, just take the derivative of both sides. So you take the derivative of both sides, you're gonna get, you know, something, I'm gonna write it. You're gonna get d dx f of x equals d dx, all of this nonsense over here. It takes so long to write these. That's kind of like the worst part of this section, is how long it takes to write anything. So you take the derivative of both sides. If you take the derivative on the left, you're going to have just f prime. And if you take the derivative on the right, you're going to get whatever you get. Because of the way I wrote it, I can actually say what the derivative is. I'm not writing it in any special way. I'm just taking the derivative using the power rule here. You get a series. And the point that I'm trying to make here is this, is that you just get some series over here. You're just going to get, like, I know that these are called C's, right? But, like, I could say, like, that C1 I could actually call, like, a new D0. And then the C2 times 2, right, because there's a times 2, that could be, like, a D1X. And then the 3C3 could be, like, my D2 that's on the X squared, and so on. And the point is at this point, you have a power series equal to f prime. Is equal to f prime. And remember, in the previous section, we had a theorem that said Taylor series are unique. And so if you have a power series equal to f prime, it must be the Taylor series, or in this case, the Maclaurin series. So that must be the actual Maclaurin series for f prime. And that's the whole idea here. So as an example, here's what you could do with it. Here's one of the things you could do with it. Let's see, what do I want? Yeah, okay, so let's try this. So let's say, you know, let sine x equal, this is the series for sine x. I'm writing it. I'm not going to write out the formula for you. That's a factorial, x to the 5th, 5 factorial, minus x to the 7th, 7 factorial, plus dot, dot, dot. Right, so that's the series for sine. So take a derivative of both sides. And we have to take the derivative of everything here. So what's the derivative of sine x? It's going to be cosine x, right? Derivative, d dx. Now, what are we going to get on the other side? The derivative of 1 is 0. Okay, you know what? I'm really sorry. I have no idea what happened here. This is the series for sine. I don't know why I started with 1 minus. It's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So sorry for that. So now let's take the derivative. So the derivative of x is 1. The derivative of 3x squared, of x cubed is 3x squared, 3 factorial. The derivative of x to the 5th is 5x to the 4th over 5 factorial. 7x to the 6th over 7 factorial plus dot dot dot. But you can simplify these because, like, for example, 3 over 3 factorial is 3 over 1 times 2 times 3. But 3 over 1 times 2 times 3 is actually 1 over 1 times 2, right? Because you can cancel the 3's. And that's just 1 over 2 factorial. So the point is 3 over 3 factorial is 1 over 2 factorial. So do all that canceling and you get x squared over 2 factorial there. Here on this one, you cancel the 5, oops. You cancel the 5 with the 5 factorial. You end up with a 4 factorial in the denominator. 7 in the 7 factorial will give you x to the 6th over 6 factorial plus dot dot dot. And if you compare this, this is going to work out to this formula here. It is negative 1 to the n, x to the 2n, 2n factorial. And this is what you already have in the table for the cosine function. Table of series, right? So you can actually take the derivative of the sine series to get the cosine series. Interesting, yes? Okay, here. All right, we have to do one more thing here. So let's try this. This is going to be, I think, the last one we do because it's going to be the last one I have time for right now. So here's one last example. And this is really going to show you something that you need to understand. So they're going to do something like this. They're going to say, find the first 4 terms of the series for, and it's going to be like this. I think this is it. 4 over 1 minus 2x squared squared. And it looks like a really hard question, 4x, sorry. And that looks like a really hard question. But there's a specific way to go about this, and you wouldn't necessarily know this. So I'm telling you, first of all, this is the derivative of something. Okay, I'm telling you that. What? Is it the derivative of? I'm not writing out that sentence, but what is it the derivative of? Well, to find out what it's the derivative of, take an antiderivative to find out. Right? I know that I can get a series by taking a derivative, but what if I don't know what to take the derivative of to get me this? That's a problem. So we need to do an antiderivative here. So you write this out as an integral because we're doing an antiderivative. You'd have to do this with the u substitution. I'm going to do it quickly. U is 1 minus 2x squared. Du is negative 4x dx. So du over 4, actually no, just negative du is what I want, that's all. Negative du is 4x dx. So I put that into what I have here. It's the integral of 4x dx, which is negative du on top. On the bottom, it looks like u squared. So I have a negative integral of u to the negative 2 du, which to do that integral, it's the power rule. You add 1 to the power to get negative 1, divide by the power to get over negative 1, plus c, which turns out is just 1 over u plus c. So it is 1 over u, which is 1 minus 2x squared, and then plus c. Now, the point of this is this. Here's what you were supposed to get out of this. The derivative, stop that. The derivative of this must be this. Okay? A key fact. If you don't know that, you can't do the problem. Okay? So what you're going to do is this. You're going to start with, now we can go to write the series. Oops. Okay, so start finding the series. So the way you're going to start finding the series is you're going to write this. So you're going to start with the geometric series, which is the one top on my list. 1 over 1 minus x is the summation of x to the n. Okay. All right, let's do this. So you're going to start here. 1 over 1 minus x is, it's this series. 1 plus x squared plus x cubed plus dot dot dot. Okay? So that's where we're starting. Now what we're going to do is we're going to make this series first. How are we going to do that? You're going to take this 2x squared and put it in for x. So if you put 2x squared in for x, you're going to get 1 over 1 minus 2x squared is 1 plus 2x squared plus 2x squared squared plus 2x squared cubed plus 2x squared to the 4th plus dot dot dot, right? So we're getting there. 1 minus 2x squared. So what do we have? I'm going to work this out. It's 1 plus 2x squared plus, if you work this out, it's 2 squared x to the 4. And then the next one is 2 cubed, that's 8, x to the 6. And then the next one is 2 to the 4th, which is 16, x to the 8th, dot dot dot. So we have a new series. Now, the reason I wanted this series was because of what we did up here. Take the derivative of the series to get the 4x over 1 minus 2x squared squared. So now we're going to take the derivative. So you're going to do a d dx on both sides, right? d dx both sides. So d dx of this, d dx of the other side. I just realized I can use cut and paste. What a time to be alive. Do it again. All right, cool. So we take these derivatives. Now the point is that we already know what happens on the right. That was why we did all that extra work ahead of time. It wasn't obvious. I know it wasn't obvious why we were doing that integral, but it was so we would know this derivative right here. Over here, we just take the derivative. So literally, you just take the derivative. So the derivative is going to be derivative of 1 is 0. The derivative of 2x squared is 2x. Okay. The next derivative is going to be 2 to the 2. And then the derivative of x to the 4th is 4x to the 3. And then the next derivative is going to be 2 to the 3. And then 6x to the 5. Next one's going to be 2 to the 4. And then what's it going to be? 8x to the 7. And keeps going. And you can do a lot of stuff with this. So first thing you can do is you could actually figure out what these numbers are. So you could say it's 4x plus 4 times 4 is 16, x cubed, plus the next one's 8 times 6, that's 48, x to the 5th. Next one's 2 to the 4th, which is 16 times 8, that's 128, plus 128, x to the 7th, plus dot dot dot. You could do that. I think that's actually what the problem wanted. I think this is actually what the problem wants. Make a box, dummy. Man, wouldn't make a box. I think this is actually what it wants. But you could even actually come up with it as a formula if you're very clever. Well, not that clever, but pretty clever. What you'd have to do is try to figure out what the pattern is here. So you'd have to think about it this way. First of all, this is gone, forget it. So that would make this the n equals 0 term, this the n equals 1 term, this the n equals 2 term, and this the n equals 3 term. So if you wanted a formula here, you would see that when n is a 0, that's a 1. When n is a 1, that's a 2. When n is a 2, that's a 3, right? So there's a 2 to the n plus 1 in there. Okay, so that's interesting. Then you've got these numbers in front. Not in front, like a 2, and then a 4, and then a 6, and then an 8. Well, looking at those, they are, that's an even number there, right? Like it's a 2 times something. Like this one is a 2 times 1, 2 times 2, 2 times 3, 2 times 4. So that actually looks like it's 2 times n plus 1. Interesting. And then you have the x, and the power on the x looks like it is counting up by 2's. So that's a 2n and plus 1 because it starts at a 1. So you could actually figure out what that series is as a formula here. And then I guess you would combine the two 2's there, and you'd have 2 to the n plus 2, parentheses n plus 1, x to the 2n plus 1. And I don't think you have to do this specifically on this problem in the book, but it's an interesting thing to be able to do. All right, so that's it for this lecture. I went over. It's my office hours now, and I'm not there. But I will talk to you guys later. See you next time. I'm going to put up an extra... Sorry about that. Probably killed your eardrums. I'm going to put up an extra couple of problems in a separate video. Yeah.